Hello and welcome, this is Harshit, and now we will see the report for the fourth experiment of Signal Systems Laboratory. So, our aim in this experiment is to perform linear convolution of input discrete time sequence at impulse response of LTI discrete system with zero initial conditions. That is, if the input is 0 for t less than 0, then output is also 0. Here, these are systems which we have been given, and we have to find the impulse response for them and to study the system on real world signals, sketch the outputs, see the observations, and move the trend from our output, and also see the properties of the signals. Coming to convolution. Convolution is a mathematical operation used to express the relation between input and output of an LTI system. It relates the input, output, and impulse response of LTI system, which we will see now. Here, we use the time invariance and linearity property to get our output, which is yn equals to xn convoluted with hn, which is given by summation of k equals to minus infinity to infinity xk h n minus k, where x is our input signal and h is our unit impulse response shifted by k units. Now, coming to our MATLAB code for that. Here is the function for convolution. Here we first load our input signals using the load command, and we declare two matrices x and h to store to perform convolution, and we store the output in the output variable. We use for loop to perform convolution multiplication step by step, and it is achieved in this step, which we do for all I minus j plus 1 greater than 0. So first, coming to our input plots. Here we load our input signals and plot them using the plot and subplot commands to get the visual representation of our input signals. These are our input signals x2, x3, x4 and xb2, where on x-axis, on y-axis we have the amplitude, and on x-axis we have the n values. Now, coming to our first system, which was this yn equals to 1 by 3 xn plus xn minus 1 plus xn minus 2. Here is the code for this signal. First, we get a visual representation for our impulse response using the canonical delta function and its shifted versions, and we plot them using the stem command. Then we create a matrix h equals to 1 by 3 to perform convolution using the convolute function, and we pass the input signals for as one of the arguments and the impulse response as the second argument, and we plot them and we get our convolution, which is just loading. So this is our impulse response, which is non-zero for n equals to 0, 1, 2 and 0 for all values, and this is our convolve functions, convolve output signal y2, y3, y4, y5, yb2. Again, y-axis as the amplitude and x-axis as the n values. Now, coming to our second system, which is this. Here we use different values of m, 25, 50 and 100, and plot them and do the convolution. First, let's see the impulse response for all values of m, which is 25, 50 and 100. Here we use a matrix to get our impulse response, and which is 1 for the given range and 0 otherwise, and we plot it to get the visual representation of our impulse response, which is this. It is 0 for some values depending on the value of m, and 0 otherwise. Coming to our code for that, we just create our impulse response using repeat element command, which is of size 25, and convolve with help of our convolute function for different inputs x2, x3, x4, xb2, and plot them. This is our output convert signals. This is for m equals 25. Now moving on for m equals 50, which is a similar code except that here we use repeat element 50 and we get our similar output signals. Yes, it is similar to our m equals 25 one, but just a bit more smooth. Similarly, we can do for m equals to 100 and see the output signals, which are this: x2, x3, x4 and xp2. Here we use repeat element 100. Now coming to our third system, which is this: yn equals to xn minus 1. Here first we get visual representation of our impulse response by using the canonical delta function as earlier, and then we use the convolute function to get our convolution, and we can see them now. These are very similar to our earlier functions. So here is our impulse response, which is non-zero for n equals to 0 and 1 and 0 otherwise, and this is our output signals: x2 for input x2, x3, x4 and xp2. These are our output convert signals. Coming to our fourth system, which is this: y equals to half of xn minus 2. Here also we use canonical delta to get the visual representation of our impulse response, and similarly we create an vector h and convolve it with our different input signals to get our output signals. Yeah, so this is our impulse response, which is non-zero for n equals to 0 and 2 and 0 otherwise, and this is our output convert signals for different inputs. As you can see the trends here. Now coming to our next part of this, we saw the impulse response and the performance for different systems and the outputs for each of the systems. Now coming to observations, as we have seen from the outputs that our system 1 and 2 allow low frequencies to pass through, so these are low pass filter, and the system 3 and 4 allow high frequencies to pass through, they are the high pass filter. Now we will remove the train from the baseline vendor or train from our signal. Coming to the code for that, yeah, this is the code for that. Here it is for system 2, which was this, our system 2, and the code is here. Here we first create our impulse response repeat element 1 by 100, and in this first we convert our signal, then we use difference equation between our input and the convert signal to get our output signal without train, and we use superior zero padding in the signal depending on the value of n. So we will see the output for this. This is our input signal, this is our baseline vendor or the train which we see, and this is our output signal after removing the train. As you can see, it follows a nearly same line. Yeah, so this is how you remove train for that. Now coming to our properties part, as we have seen for our all the systems, as they are LTI, so they are linear and time invariant, and there are also bounded functions as they are not tending to infinity for any value of n. They are also causal and memory functions. So this brings us to the end of our report for experiment 4. Thank you.